The making of red blood cells is called erythropoiesis, and it's a process that is always going on in your body. Just because you're making cells doesn't mean that something's wrong, like when you make leukocytes. When you make white blood cells, you might have an infection, but your red blood cells only have a 120-day lifespan, about, right? Like that's an average. They're red blood cells, erythrocytes, they're meant to do their process for that long, and then they're meant to be removed from circulation. They take a lot of mechanical abrasion as they float around your body. They get squished through capillaries, they bump up against each other, and they're basically getting worn out like the soles on your shoes. Or like the soles on the cashmere socks that I knitted for my husband, which, they're cashmere. Why are you wearing them outside to shovel the driveway? Anyway, after about 120 days, erythrocytes, they either pop open in blood or they're removed by the spleen, which is most likely. But in order to keep your red blood cell count in equilibrium, that means that more of them have to be continually made. So where are they made, you ask? In your red bone marrow. And this is the bone marrow that's present in most of your flat bones, like your hip, your sternum, and even your skull bones. Even though the picture that I have here is of a long bone, you would have red bone marrow in your long bones, more of it younger in life. So this bone marrow that is present in most of your flat bones, as you age, red bone marrow converts to yellow, and it lowers your ability to replenish red and white blood cells. That's just a fact of aging. To make red blood cells, you need to have the breakdown of other red blood cells, right? To make red blood cells, you need red blood cells. It's kind of like terracotta. What do they make terracotta from? Terracotta. In that way, you're just constantly recycling a whole lot of cell membrane components and the hemoglobin and the iron and all of your juicy things that are contained inside an erythrocyte. Although your organs are very good at recycling, there are a few things that you have to continually provide in your diet. The two major vitamins that you have to be getting to make red blood cells are B6 and B12. And a lot of us don't get the amount of B12 that we think we're getting. We will also talk about pernicious anemia, which by definition is a lack of B12. It's important to realize that a lack of B12, it can happen for more than a few reasons. Not only that you're not getting it into your diet, but you could have an autoimmune disease, you could also have a gastric disease. Iron, which is also required, is constantly lost through the recycling of bile. So we're going to see how the recycling of bile plays into erythropoiesis. And so you're continually needing to have foods with iron in them, right? So you have to obtain the iron, you have to obtain the B vitamins, and then all that you need are eggs and fish. If you don't eat eggs and fish, any of these wonderful vegetables down here will provide you with what you need. What you need from these things are amino acids. And you're creating amino acids every time you take in protein-rich foods. Your body's capable of making 18 out of the 20 existing amino acids on this earth. And if you don't eat animals containing the other two, then you have to take care to obtain these other two amino acids, which can easily be done by eating wheat bread and hummus. Okay, let's get to our target here, which is our erythrocytes. Erythrocytes are red blood cells, and they, along with other formed elements, right? Remember that word, formed elements, which are the cell or cell components in blood. Along with other formed elements, they originate from these hematopoietic stem cells. These had a different name recently, but I cannot recall that. This hematopoietic stem cell is like a master stem cell, and what it does is it divides into two other stem cells. We have a lymphoid stem cell and a myeloid stem cell. These can also be called progenitor cells because they actually divide and lead to fully functional cells. Um, the myeloid stem cell makes everything that the lymphoid stem cell doesn't. Kidding. The lymphoid stem cell makes lymphocytes, B, T cells, NK cells. And the myeloid stem cell, it does make everything else. Neutrophils, eosinophils, basophils, monocytes, megakaryocytes, and red blood cells. Among the white blood cells, neutrophils are the most abundant cell type of white blood cells. Then there's monocytes, and then there's basophils and eosinophils. This here is a megakaryocyte. Your book refers to colony forming units. And usually that's just an aggregation of cells with all the same different cell membrane proteins. So they all kind of have like the same identity, right? So some of these have individual identities with cell membrane proteins. And while these are developing, you'll get groups of cells all kind of aggregated together. As red blood cells go through their maturation life cycle, the protein receptors and the enzymes contained in the cell change in composition. So it's almost like they become new cells with a new life stage. Mostly when cells are developing, it's the intercellular receptors that are the most important in defining a cell. Okay, so we understand colony forming units can be aggregates of cells that have the same cell membrane proteins coming off of them, which means that we can also call them committed cells. And in this case of an erythrocyte, any committed cell is a cell that it is gonna become a red blood cell, right? It's committed, right? It might not be a red blood cell yet, but it is committed. It has acquired receptors for a hormone called erythropoietin, which is abbreviated EPO. EPO receptors define these cells as cells that will become red blood cells. Other cells arising from myeloid stem cells do not have EPO receptors. Once the cell has committed, it can now respond to EPO, and it does respond to EPO. The cell creates organelles such as a nucleus and an endoplasmic reticulum, and it becomes what we call an erythroblast. And there are a few stages to an erythroblast. This here is an early erythroblast that I just labeled. At first, the organelles are used to make the hemoglobin protein. But when enough hemoglobin's been accumulated, and that's what this protein is right here, this is hemoglobin. When enough hemoglobin has been accumulated, the erythroblast, it pukes up all of its organelles, which is what you can see here, in exocytosis, right? It does that to make room for all of that hemoglobin. And therefore, late erythroblasts are usually a little bit larger than the other cells in the sequence. Then there are also reticulocytes. Reticulocytes are not fully matured red blood cells, but they have left the bone marrow and they have entered into circulation. They circulate for about 2 weeks and they finally develop that beautiful bioconcave shape that's characteristic of erythrocytes. That bioconcave shape that maximizes surface area to volume ratio. At that point, when their surface area to volume ratio is perfect for the bioconcave shape, they're now considered to be fully matured erythrocytes. And they remain in circulation for about 120 to 128 days, and then they get broken down and the process repeats itself. Erythropoietin is an amino acid hormone that's made by the kidney. And there are cells in the kidney that are called granular cells. They can be triggered to release erythropoietin in 3 ways. If the kidney itself receives hypoxic blood, low oxygen blood, depriving nephrons in the kidney from oxygen, then the kidney responds by releasing EPO. There are chemosensors in your lung that can detect low oxygen status, and these chemoreceptors feed back to the granular cells in the kidney and provoke them to release EPO. If your lungs have damaged lung surfaces and those cells are secreting certain chemicals like interleukins and cytokines, there are also chemoreceptors that can feed back to the granular cells of the kidney, triggering it to release EPO. Since EPO is specifically designed to increase the rate at which you make red blood cells, the target of EPO is all of your committed cells in the red bone marrow. So erythroblasts, reticulocytes, hematopoietic stem cells do not have these EPO receptors. Myeloid stem cells do not have the EPO receptors. And these two types of cells are incompatible or incapable of being provoked by EPO receptors to increase red blood cell production. Only erythroblasts and reticulocytes have EPO receptors and are capable of responding. As a result, EPO increases hemoglobin production, but it also increases red blood cell production in general, and it speeds them both up to be about 10 times the regular rate. So all of these reticulocytes, like all at the same time that are currently in circulation, they all mature very quickly into optimal bioconcave shapes within days. But the true benefits of EPO, it's not going to be felt until all of those erythroblasts that are currently in production mature and enter circulation. Normally, that can take 2 to 4 weeks, but we can speed that up by 10 times with EPO. At the same time that we're increasing red blood cell production, we also have to increase red blood cell breakdown, right? This has to be in equilibrium. So the spleen also responds to EPO, and it does that by creating more macrophages that are capable of breaking down the red blood cells. And the iron and the bilirubin are processed by the liver, hopefully more quickly, most of it being returned to red bone marrow. But the reality is that some of the iron and the bilirubin will be lost in feces. So if you want to increase red blood cell production, you also have to increase the things that are required for it, like iron, B6, and B12.